all the speakers come up towards the front and hang out here, and we can discuss anything we want regarding volatiles. So I can see the bad rush to the front. So, okay, well, I don't know if we're going to get to the front. And having me as a volatile expert is a dangerous thing. But why don't we ask this? Are there any questions or topics that we think would be sort of good for discussion? And we have a lot of different things we can do here. I see someone raised their hand.
Well, I have a question about the micrometeorites.
Yeah.
Depositing water on the planet.
Oh, we're going to give you a microphone.
Thank you. The question that I have is the volatility of the water in the micrometeorites as it approaches the planet, is there any consideration to it desiccating or sort of evaporating just from the sun before it hits the moon, but more as it approaches the moon?
Well, I see Dana hiding in the very, very back, and this seems like her kind of question. While she slowly walks up here, I would guess that it's probably not ice on the micrometeorites. It's probably some kind of hydrated silicates that then when it hits and it vaporizes, that's where the water is. But I'll let Dana give the real answer. So.
Yeah, well, I mean, I think that's the question that Andy Rivkin was getting at after my talk was, there are different populations of the micrometeoroids and they have different contents of water. And so, a lot of them that are, in orbit or, about 1 AU, they'll hold on to their hydrated minerals, but they're not going to have like ice in them like a cometary dust trail sort of thing. But the cometary stuff may be a little bit icier.
We have other questions.
I just had a quick clarification for Dana. So you're using your Monte Carlo model and you're assigning a temperature and a bulk velocity, and the temperature gave you a thermal velocity distribution. And so you were just varying those, and then you backed out from whatever fit with your observations the size of the micrometeoroid that you think was causing those impacts.
Yeah, so I tried a couple different velocity distributions to see how much of a difference there was, and then when I did the final calculation, I only used the 5000 K zero bulk speed for those calculations. But it's going to be different depending on what velocity distribution you get, because the the distribution of density at altitude that you measure changes as a function of that. But just due to the fact that we see things with the NMS, and that having a bulk velocity makes it so that a lot of the particles are outside of our NMS field of view, makes me think that one of those cooler or the zero bulk velocity distributions is probably what's really happening.
Well, since you're at the microphone, I'll ask you a question. So, in some of the work I've seen on micrometeorites, so they've actually they find these in Antarctica in the water wells of the bases there, and they've done like size estimates. And we also have the LDEF spacecraft, and we would have the Genesis spacecraft. And it seems like most of the mass in micrometeorites is around 100 microns or of that order. Is that a consistent number with what you're finding with your results in terms of what's actually producing the water hits?
So if a 100 micron micrometeorite hits the moon, the density of water at altitude is going to be too low for NMS to see it.
Okay,
so we can only see the things that are tens of grams and bigger.
Okay, so well, this actually raises an interesting follow-up, which is related to something that was in my talk, is that when you have a micrometeorite hit the moon, how much water do you lose? And I can imagine, it sounds like what you're saying is that could be a size-dependent number. If 100 micron hits and it loses water, it doesn't actually get up to where you can detect it. While if something larger hits, you are probably losing some water because it's getting to higher altitude, right?
Well, actually, I mean, when I said that, I was scaling linearly. So saying that all the meteorites have the same fraction of water in them by mass, and that the density at altitude scales with that mass linearly. So there are effects like, if the velocity is different and you're going to have different energy, it's going to affect your velocity distribution. So that's more wiggle room.
Okay. So how do we test that then? How do we know how much water? Because this, if we believe the micrometeorite story, then it matters how much escapes in a given impact, because that's not a number I have a feeling for.
It does, yeah. And so, I mean, you can conceive of an instrument that would fly in orbit around the moon and detect water and have some different look directions so that you could try to constrain that velocity distribution.
Okay. Other topics, other questions?
So, as you're showing that it might be hard with comets and such to make some of the ice deposits, and I still don't quite follow all that argument, so I haven't seen anyone quite as pessimistic about comets and asteroids before. But I'm also curious, if we're okay to have these ice deposits built up over billions of years, what about on the moon and Mercury, indigenous forms of water, released from volcanism on these bodies, and do we need to consider these more in our source than we've been talking about? You find, and I know people have been looking at the Mare basalts and seeing, oh well, this chlorine isotope tells us that there was a 1,000 ppm water or something to be in the Mare basalt to begin with. It's a lot of volume of water that you could release as well, and we should compare those numbers.
I think you have to worry about all that. I mean, what I did was not very far from a back of the envelope calculation in reality. I mean, I'm putting the best numbers I can. Yeah, no, I'm not trying to defend my stuff, but I mean, at some level, so in terms of asteroids and comets, you saw the numbers I put in, and the numbers that come out of, like, how much water does a comet deliver, how much water does an asteroid deliver, depends a lot on what you choose for the efficiency of how much stays behind. If you change those numbers, you could probably get different results in some fashion. Those are the numbers in the literature, but maybe they're right or wrong. I don't know. In terms of indigenous sources, well, let me ask you this, or I guess this is something that I think comes up, is that we're talking about the permanently shadowed regions on the moon. How old are the craters that have been in permanently shadow? I mean, let's say if they formed 2 billion years ago, then that reservoir is 2 billion years old, and or if it formed 3.5 billion years old, then you have a chance to get a lot of Mare basalt volcanism water. So it depends. Again, if they're younger, you're not going to get volatiles from the Mare basalts. If they're older, you might. And then the question is how much you get from that, and then how do you tell the difference or test that? I don't know. That's why this is fun, right? So, but go ahead. Actually, you can come up here. You can. Well, okay.
At LPSC, I had a poster on that, and what we did was do dating of the host craters for the polar ice deposits on Mercury, of the youngest craters that hosted, and that was based off of Luisa's new cratering catalog for Mercury. And what we found was that the youngest ice hosting craters were on the order of like 3.5 to 3.7 billion years old for Mercury. So that, I mean, it provides a very maximum for like what ice could be inside of it, but it's still very old. But it does coincide with the period of heavy volcanism on Mercury.
Yeah. Do we have the same estimate for the moon?
No.
That's a great project for someone, actually. It's like, how old are these permanently shadowed regions? I don't actually have a feeling for it. So. Do you remember what he got?
3.4 or so.
Okay, so they would have seen some of the Mare. So Mare basalts flowing at the same time. If they're producing water, it's possible that water could get into the traps. So okay. So we don't have lines of questions. This is good. Go ahead.
Hi. So you had quoted in your talk a mass of ice in the permanently shadowed areas of the moon, and I'm sorry if I missed that from elsewhere, but how did that mass get determined? Because I know that we can detect it from the surface, but I didn't know that we had a constraint on the depth of how far down that went, and so I didn't know how you got your total for water.
The way I got that was I looked in papers, and yeah, I didn't independently calculate that. I think at least one paper was from it must have been a messenger paper, and they were trying to make an estimate of the total volatile abundance they have there. But you saw the range. It had a couple orders of magnitude in it. I think for the moon it was something similar. I think it was probably some estimate from it was probably from L-Cross or something like that. And they're trying to extrapolate to various things, or they were looking at the hydrogen signature and saying, okay, yeah, okay, so. Okay. Yeah, that would be great, because I remember when I looked through this, I wasn't, again, these numbers are a couple years old, and we've learned things, and you worry about it, but it's the only number you can find, so you have to use it. So, yeah. So, go ahead.
Okay. A question to Amanda's presentation. The method was very interesting, and then actually you are just looking at the soil came from the sample underground. Okay. Now I'm wondering if you can quantify the how wet or how hydrated it is. I did not quite see how you can quantify that one, whether this is either yes or no, or just how much. Okay.
Yeah, so we should be sensitive down to about halfway percent water. Anything above that, any concentrations above that should be discernible with a spectroscopy just by measuring band depths. And of course, I'm making it sound a lot simpler than it is. There's probably not just going to be water. If there's water, you'll have to, model any other constituents that might be coming out with the water. But essentially, it comes down to measuring band depths. And we should be able to, well, we're required to be able to measure down to half a weight percent. Sometimes we can do better. Don't quote me. And then, but up beyond that concentration, yes, we should be able to quantify.
Go ahead.
In part, answer to address one of your questions about age.
Yeah.
One, in addition to dating the craters themselves, which is outside of my wheelhouse, one of the limits, or current limits, is the spatial distribution of the hydrogen. And we keep talking about it locked up in PSRs or craters or otherwise. And that may not always be the case. We're limited with currently poor spatial resolution, and looking to the next generation beyond instruments that have already been selected, it is probably necessary to think about doing these measurements at a level of sensitivity to about 50 ppm hydrogen with spatial resolutions of between 5 and 10 kilometers. Better is better, but that is sufficient to start being able to make these correlations between hydrogen concentrations and craters that are better dated. And some instruments along those performance lines are on paper and could be a possibility for the next generation. I just think it's really important not to look forward to better hydrogen measurements, both in sensitivity and spatial distribution, which in conjunction with some of these other measures can really separate out some of these questions.
Okay. And in terms of crater ages, well, this is a question for like Michelle Kirchhoff and the rest. I'm not sure how easy it is, because I think some of the craters you're trying to date are small. So there's probably things you could do, but it actually is a really good question for someone. I think we're just about ready to break. Let me just ask one last question and then we'll break the discussion. So one thing that I think no one's talked about is that if you imagine you put water into a permanently shadowed region, 3.5 billion years ago or 3 billion years ago, is there an attrition rate? Do you lose it over time, or once it's there, is it there essentially forever?
Yeah, I mean, there are processes that get rid of it, including, sputtering and photo desorption and impacts. All those things kick it out. But when you get a little bit of a cover on it, it can help protect it. And that's assuming that you're talking about the really cold places where, it's not going to sublimate.
So does it have a half-life, or is it essentially just, what does it mean? Do we have any feeling for how long, if you imagine you put a bunch of stuff there 3.5 billion years ago, how much would be left today?
It depends on how much stuff you put there, because the thickness matters.
Okay.
I have a paper on it I can send you.
Okay. So, well, as I used to say on Car Talk, you've managed to waste a perfectly good 15 minutes in this discussion. So, but thanks very much for attending the session, and thanks for the discussion period. And we're going to move over to have the joint, League SBAG meeting, and that starts in 5:20. So, we've got a couple minutes.